Hello, my name is Will, and this is my Lab 4 report. Firstly, I will do a quick introduction. In this lab, we built circuits and predicted their behavior using our physics knowledge. For this lab, it was essential to be familiar with the loop rules, energy conservation law, and RC circuits. In this report, you'll see that the predictions are often in line with outputs from the circuits themselves. I will also discuss why this may not always be the case if these circuits were to be built in real life rather than simulated. In part 1 of this lab, we were tasked with manipulating a circuit and recording answers to questions about the circuit and said manipulation. The starting form of the circuit is shown above. I'll go over each of the answerable questions as the lab continues. Firstly, I was asked to predict the current of the circuit. I can do this by using I equals V over R. This returned an answer of 0.0204, which is the same returned by the ammeters. Next, I was asked what would happen if the ammeters reversed. This changed the sign of the results. Problem 4 asked me to connect the voltmeter in series with the circuit. This caused the voltmeter to read 3 volts and the ammeter to read 0 volts. This is a result of the voltmeter having an infinite resistance preventing current flow through the ammeter. For number 5, I was tasked with measuring the voltage across each of the components in the lab. As you can see, measuring across the 47 ohm resistor gave a voltage of 0.96, while the 100 ohm resistor gave a voltage of 2.04. The battery gave a negative voltage of 3. The signs don't matter as much as long as they're all measured in the same direction. This will cause them to sum up to 0 in line with the loop rule. All other node-to-node measurements were 0. The graph here shows the potential differences across the circuit. You can see the voltage grow with the batteries and drop with the resistors back to 0. Next, question 9 asked why the voltmeter alters the behavior of the circuit while the ammeter doesn't. This is because the ammeter has no resistance in a simulation, while the voltmeter has infinite. Question 10 asks how the ammeter acts when the voltmeter is attached in parallel. It has no change. However, if another ammeter is attached in parallel, they both change to 0.06 as a result of the loop rule. Question 12 asks us to calculate the resistance of the circuit components using their voltage difference and knowing the current. The 47 ohm resistor had a voltage difference of 0.96, which once divided by the current, 0.0204, is 47. Following this procedure for the 100 ohm resistor, it also came out to 100 ohms. The wire and ammeter had no resistance as they had no potential difference. In part 2, we were tasked with investigating RC circuits, and the results were as follows. While in a circuit with both the battery and capacitor, the light starts to get bright and progressively dims as the capacitor charges. The increasingly charged capacitor limits the flow of current, dimming the light. When the battery is disconnected, the capacitor is able to discharge, once again turning on the light, and it begins to dim. When the capacitor is reconnected without the battery, the current flows the opposite direction as before. Next, I measured the time it took for different ohm light bulbs to charge and discharge with the capacitor. With the 10 ohm bulb, it took roughly 5.7 seconds to charge and 9.2 seconds to discharge. And with the 20 ohm bulb, it took 8.2 seconds to charge and 20 seconds to discharge. In part 3, we went through a series of steps to find the RC value for a circuit with a 30 ohm bulb and a capacitor. Here you can see my process for finding the RC. I marked the time and voltage readings from the simulation and converted them into a version that was the natural log of voltage over the natural voltage, which was 3 volts, and plotted that against time. Since we know the slope of this plot would be -1 over RC, I used Excel to find the slope and solve for my RC. My solved RC was 6.09. This is relatively close to what it should be. We know that tau is equal to resistance times the capacitance, which we are given as 30 and 0.2. This means that the predicted RC would be 6. The difference is likely due to the trouble of correctly timing within the circuit simulation. And finally, I will end by answering questions. Online, the ammeter has no resistance. This is impossible, and in real life, it would likely affect the results of many of the procedures. It would need to have some form of minuscule resistance, especially if it has a readout of some form. The second question asks about the behavior of an RC circuit with no resistance. Theoretically, this would give an undefined slope for our time by natural log of voltage over natural voltage graph, as the slope is -1 over RC with the resistance in the denominator, meaning 0 would be in the denominator, making it undefined. This would not happen in real life, as it would be impossible to have a zero resistance circuit. The wires themselves have some form of minuscule resistance, and anything greater than 0 would be enough to prevent the slope from becoming undefined. Thank you for listening.